All right, AP Physics, here are your next most missed questions for the Newton's Law assignment. I'll jump right into them. This problem asks you to evaluate someone pulling themselves up using a little bucket and a pulley. The boy stands large bucket, and the combined weight of the boy and the bucket is W. The bucket is lightweight rope, so we neglect the weight of the rope, and it extends over a simple pulley. Here's how you evaluate this one. It says, as the boy pulls himself upward, he applies force F to the rope. Which of the following claims indicates the correct relationship between F and the weight of the system? Well, if he pulls up on this rope here, remember, tension in a rope is the same all the way throughout the rope. So whatever he pulls with down here with your force, we'll call that F, that's going to be the same force all the way throughout this rope. And so if he's applying that force to the rope, this would be the free body diagram for the rope. That means the tension in the rope equals F. And if you look at the free body diagram for the boy, or just treat this as one big object here, well, that's going to be an object with two forces on it. There's a force pulling on this side of it and a force pulling on this side. In other words, the rope connects to that object twice. So I'll have F up, and I'll also have F up on this side for each side of that rope. In other words, the boy only needs to pull with 1/2 of the weight force. And if this is 1/2 of W and this 1/2 W, they both add up to W. And he could keep himself at constant velocity or not moving at all. So let's go back to our problem here. As the boy pulls himself upward, he applies a force F to the rope, which the following claims indicates a correct relationship between F and W. Let's evaluate the one that they say is correct. A, F has to be less than W because as the boy exerts force downward on the rope, the tension of the rope is pulling up on the boy and up on the bucket. So there's your two forces, the and right there. This is your correct one. Force has to be actually 1/2 of it to remain at constant velocity. Why aren't these ones with the less than correct? Look at their explanation here. F has to be less than W because as the boy exerts a force downward on the rope, the tension in the rope pulls up on the boy. This is in addition to the normal force the bucket exerts on the boy, thus reducing the force. It's not the normal force, it's the tension force of the rope coming around on the other side of the bucket. F less than W because the boy exerts a force downward on the rope. Tension in the rope pulls up on the boy, which reduces his weight. His weight force is not going to reduce. This will be the same. That comes from Earth's gravity pulling on him. So it doesn't reduce his weight. It just pulls up on him. So that's incorrect. And then the other ones don't have the correct choice for the relationship between force and W. Our next one, an experiment is to be conducted to determine the coefficient of kinetic friction between a block and a flat plank of wood. The plank is tilted at an angle theta, and the block slides down the plank. It is observed that a block of mass m slides at constant speed. This should tell you something about the acceleration. Constant speed means A equals 0 meters per second squared. And that should tell you something about the net force. F net must be equal to 0 newtons. What quantities must be measured in order to calculate the coefficient of friction? Well, to evaluate this guy, I was surprised this was one of our most missed problems because we did this lab, exactly this lab. So let's take a look at how you evaluate this. You want to draw a free body diagram first. The only forces acting on it is the force of gravity, the friction force, and I didn't write it in here, our normal force. And our normal force is equal and opposite to the vertical component of your force of gravity here. So what do we care about? Well, the force of friction has to be acting up the plane and have the same magnitude, just opposite direction, as the component of gravity acting down the plane. If those two are equal and opposite to each other, then our net force down the plane is 0, and we have a constant velocity. It doesn't matter the size of the block. Every block would do that. So if we set up an axis system, our y direction being vertical, I'll draw my normal force back in here, and the x direction going down the plane, we can say the force of friction is equal to the x component of the force of gravity, and the x component of the force of gravity can be solved for using your angles, and you get mg cosine theta times mu equals mg sine theta. And mg sine theta would be this component. If you don't remember how to break down these triangles, you draw this value here, and this is theta, and sine of theta is what would give us the component going down the plane. Mg cosine theta, this is your normal force. The normal force has to be equal and opposite to this component of your force of gravity going down the plane, and so mg cosine theta is how you solve for that component. So this is your normal force times mu equals mg sine theta. Mg cancels out on both sides, and then you can solve for mu, and you get sine theta over cosine theta, which is tangent of theta, which means all you need to do is measure this and you can calculate your mu value. And that's what we did with our lab as well. Our next one, the rope and pulley system of negligible mass shown supports a block of weight W that is at rest. If the tension throughout the rope is uniform, what is the reading on the spring scale? Well, let's just take a look at our free body diagram here. It says that it supports it at rest, and that means that we're at equilibrium here. So our block, our net force on this block has to be 0. So if I draw a free body diagram for a block here, we have W going down. How many forces do we have going up here? Well, let's just count them. Everything that's attached to this system, I'll draw a block around my system. It's everything crossing this line here. So we have 1, 2, 3, 4 forces going up. And so 1, 2, 3, 4, all 4 of those forces are equal to your tension. And your tension is going to be, if it's at rest, these have to be equal. So tension is going to be equal to T equals 1/4 of W. If that was true, then this would be in equilibrium. Well, if T is 1/4 of W, if we go back to a spring scale now, the spring scale has to keep this pulley in equilibrium. And if we drew a little box around this pulley here, our free body diagram, I'll draw it a little bit bigger here. Our pulley has 2 things coming off the bottom and 1 going off the top. Well, this is what goes to the spring scale, and the spring scale will measure the force, the tension force for this little rope going up to the spring scale. So our free body diagram would look like this. Going down, we have T and we have T. And the tension is the same all the way throughout this rope system. So we know what T is. T is equal to 1/4 of W. So if this is 1/4 of W and this is 1/4 of W, if you add those together, the force we need going vertically to keep this in equilibrium is going to be equal to 1/2 of W. And that's the tension that's going to be required. And that's what the spring scale would measure. And that's how you get B here, 1/2 of W. The next one. The velocity of an elevator moving upward between adjacent floors is shown as a function of time t in the graph above. At which of the following times is the force exerted by the elevator floor on the passenger the least? This is a really good question. And I could see questions like this on your AP test because it's hard to just Google a question like this. If you look at your graph here, this is probably how you thought about this. If you got this wrong, I want to go through this thinking. Some of your thinking is great. You're doing the physics right. So you probably thought like this. I know the net force of any object is equal to mass times acceleration. This is Newton's second law. And if the net force is equal to mass times acceleration, and it asks me about a force in the problem, then I know a small acceleration means small force. So if I want F net to be small, I want A to be small. And so I go to my little graph here and I ask myself, how do I get acceleration off of this graph? Well, acceleration is equal to the slope of your velocity versus time graph. And so I go find the spot on my velocity versus time graph where my acceleration is the smallest. In this case, it'd be 0. And I say, well, if the acceleration is 0, then the net force is 0. And then I find what time that occurs at, and I say time t equals 4. I find my answer here, which was the most selected incorrect answer. And I say I figured out the problem, I've solved it. Why is this incorrect? Well, this is not asking you about the net force on the object. It's asking about the force exerted by the elevator floor on the passenger. Well, that's only one of the forces acting on the passenger. So let's consider where that force comes from and relate this back to our net force acting on the person. So we need to draw a little diagram of our elevator. And here's our diagram of our elevator. If this is our person staying in the elevator, let's just consider the case that we just had when acceleration is 0 for the elevator. Well, when acceleration is 0, that'd be constant velocity. So it's going up at constant velocity. Or it's just at rest and staying at rest. In this case, we're not at rest, though. We have some velocity here. So we're constant velocity for a split second in time. You can think of it just like someone staying at rest as well, though. But here's our person staying on a little scale. The scale would measure the force that the floor pushes on the passenger. If our acceleration is 0, then we know the person must be in equilibrium. And if we draw the person's free body diagram, they have the force of gravity acting on them. They also have the normal force of the floor pushing on them. Well, the normal force of the floor is what the scale would read. So if they have an acceleration of 0, these have to be equal to each other. So F net equals 0. And this is what you chose for your correct answer. But this is not correct because if F net is going to be 0 newtons, then the normal force has to be equal to the force of gravity. And the scale is going to read Fg. It's not going to be the least. It's going to have relatively high reading. Okay, let's look at how we make this the least. Okay, so if we change our free body diagram here and we want the scale to read nothing, well, I'm going to reduce that normal force to 0. And if the normal force is 0 newtons, what's our acceleration? Well, if you look at our free body diagram, the only thing that's left is the force of gravity acting on this person. And if we want the normal force to be 0, then the force of gravity is going to be causing an acceleration. This is m times g. It causes acceleration of g. We'd be in free fall. So if you cut the chords on the elevator, you get a negative 9.8 meters per second squared. And that caused our elevator to be in free fall, and the scale would read 0. And that's what would happen if you're on the International Space Station in free fall as well. That's what zero gravity feels like. So how do we get this to occur in our scenario here? Well, we want the least force on the passenger. We want to be the closest to free fall. We want the most negative acceleration. And if I follow my graph here, these are all positive accelerations, and then I get a negative slope here. So on this side, my scale is going to measure smaller values as I'm decelerating. And the steepest curve is, it looks like, probably right in this region, somewhere in here. So where do we have this? 6 or 7, somewhere along that region where it's nice and steep. Where do we have that? Oh, 6 is our only choice there. So 6 would be the best choice, the steepest part of our curve. It does get a little bit more shallow here with 7. So anywhere along the straight line here. So 6 would be our best choice. What's actually happening with the elevator here? As you're accelerating upwards, the spring or the floor has to push on that person with a force greater than Fg. So I have to have a normal force greater than Fg here to accelerate upwards. As I get to my maximum velocity here, it decreases to be equal to each other. So I'm cruising at constant velocity for a split second here. And then I need to start slowing the elevator down. And if I'm going to slow the elevator down, the force of gravity is what's going to be causing my acceleration. I need to have a normal force less than the force of gravity so that the net force is in the downward direction and it starts slowing this person down. And that's what it feels like if you're in an elevator. As it goes up to the top and starts to slow down, you get that little butterfly feeling in your stomach. Same thing that happens on a roller coaster as you go over a hill. What's happening is the normal force is disappearing between you and that seat on the roller coaster or the car or whatever it is. The normal force disappears. You're in free fall for a split second, and that's what gives you that feeling in your stomach. Hope that helps for that question. That's a great question with a lot of concepts involved. Our next question, a block of mass m1 on a horizontal table is connected to a hanging block of mass m2 by a string that passes over a pulley, as shown above. The acceleration of blocks is 0.6 g. Assume that the friction and the masses of the string are negligible. We'd also have to assume that the friction between the pulley and the mass of the pulley was negligible as well. So they want to know what's the ratio of the masses m2 to m1. How to relate those? Well, this is a Newton's second law setup where we're going to use A equals the net force over m. And you could do this for each block, do A1 and A2, but a simpler way to do this is to do, and you'd have to involve your tension for that. We can neglect our tension if we do a simpler approach, and we redraw the system. We take M1 and M2, and I just move M2 up so it's directly horizontal. And I say M1 and M2 are connected, so they have to move together. And the only forces on this, there's no friction here, the only forces on this is the force of gravity on M2. Well, that's M2 times G. Let's just move that up so it's horizontal force and treat this as one big system with the only external force being M2 times G. Well, then I can set that up and say my acceleration of my system is my net force divided by the mass of the system. And if I plug that in, the mass of the system is M1 plus M2. The net force on the system is M2 times G. And the problem told me that the acceleration of the system is 0.6 times G. Well, we can solve this for the ratio now. We want to get M2 divided by M1 out of this equation. So let's get M1 and M2 on the left side. If you multiply that out, we get 0.6 times each one of these. Our G's cancel. And so I get this equation here. And now I just have to do a little bit of algebra. Move my M2s on the same side, 0.6. 1 M2 minus 0.6 is 0.4 M2. I want the ratio M2 on top and M1 on bottom. Whoops. So I divide by M1, I get M2 on top and M1 on bottom, divide by 0.4, I get 0.6 over 0.4, well, that's 1.5. So my ratio of M1 to M2 is 1.5, and that is one of your choices in your problem. Our last one here, a block of mass M is placed against an inner wall of a hollow cylinder of radius r. It rotates about a vertical axis with a constant angular velocity omega. as shown, in order for the friction to prevent the mass from sliding down the wall, the coefficient of static friction, mu between the mass and wall, must satisfy which of the following inequalities? And it gave you a list here. Let's just solve this, and you can see which one is correct in that list if you look back at the problem. But here's our free body diagram. This block has to have a normal force acting on it. Why does it have to have a normal force? If it's going to stay in circular motion here, it has to have a force causing the acceleration or the velocity vector to turn around that circle. And that normal force has to be equal to the centripetal force, mv squared over r. So our force of friction goes up here, and our force of gravity has to go down. And if it's not going to slide down that wall, the force of friction has to be equal to the force of gravity. So that's what we set up first. We'd say force of friction has to be equal to your force of gravity. And we know this, the force of gravity is m times g, the force of friction is mu times the normal force. Well, the normal force isn't given to us. We have to solve for that. The normal force has to satisfy this relationship. The centripetal force to go around that circle is equal to the normal force. And the centripetal force is mv squared over r, but they didn't give us a velocity, they gave us an omega. So we want to have the other equation for centripetal force, which is m omega squared times r. So I get mr omega squared equals my normal force. I'm going to plug this back in for my normal force right over here, and I'm going to get an equation that just has our mu values now in relationship to all of our other terms. We got rid of our normal force that we didn't know. And then I can cancel my masses, solve for mu, and you get g over r omega squared. Let's evaluate what this means here a second. That means my coefficient of static friction must be large enough to satisfy this relationship up here. The force of gravity has to be equal to my force of friction, which means this is a minimum value. If it's at least this value, then this relationship up here will exist. We'll have force friction equal to force gravity. But if you remember your force of static friction, that's mu s times my normal force. This is the maximum, Fs max. So I just have to have a maximum that at least can cover this relationship, and this would be the minimum value for that. So we can have values of mu that are larger than this, that's okay, but it has to be at least this. So we would say in inequality here, your mu value has to be at least equal to or greater than this, and we would stay in equilibrium here. I hope that helps for your problems. Let me make sure, yep, that's our last ones for this one. If you have other questions that didn't get answered, please ask, and I'd be glad to answer them.